Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the fifth part of Chapter 7, the first-order optimality conditions. Now, as we recall that we are trying to solve the constraint optimization problem with equality constraints and inequality constraints. And at a point x, we can also define the active set as the constraint that satisfies all the equality constraints strictly, okay? Now, we also can define the Lagrange function in the general form, which means that we have equality constraints and inequality constraints, and all the items, we can add them up by multiplying a coefficient lambda I. Then this will make up the Lagrange function. With this Lagrange function, we are ready to give the optimality conditions. Now, the settings are below. We assume that X star is a local optimal solution for the constraint problem. Then, we also assume some continuity about the function f and c. So we assume the objective function f as well as the constraint c, they are all continuously differentiable. Then, finally, we assume some constraint qualifications. Actually, here we assume that the LICQ holds at this point x. Now, with the settings above, we can have the first order optimality condition as follows. There exists a Lagrange multiplier lambda star such that the following are satisfied. Notice here, the condition we got 1, 2, 3, 4, 5 pairs conditions, okay? So the first one is actually the Lagrange function with respect to x. We take gradient, then we got that it must be 0. This actually interprets or corresponds to what we have analyzed before, that the gradient of function value must have some relationship with the gradient of the active constraints gradient, okay? So this is represented here. And the next 4 parts actually mentions some feasibility condition as well as some complementarity condition. So the feasibility condition actually requires that X star must be a feasible point. So equality constraint here and inequality one here. So the complementarity condition here actually mentions that for inequality constraints, we have extra requirement for the multiplier lambda. Okay, so we require the inequality constraints, the coefficient lambda I to be non-negative. After that, we also require that lambda I multiplied by ci are 0 for all inequality constraints. So this is referred to as the complementarity condition, as we mentioned before. So as we can see that for any optimal solution or any optimal problem, we can write down the KKT condition. And this system is known as the KKT condition, where the full name is that Karash, Kohn, and Tucker conditions. So we use the short name as KKT condition, which is actually the same as first order optimality condition, okay? And now let's take a look at the vector lambda I, okay? So the Lagrange multiplier vector, so this lambda I, we give it the name as Lagrange multiplier. And if you have inequality conditions and equality conditions, then this lambda should be the same dimension as the number of all constraints. Now, to give the strict complementarity condition, we need some settings as above. So we assume that X star is a local solution of the constraint problem. We also assume that a vector lambda star satisfies the KKT condition. Okay, so at these settings, we have the strict complementarity condition as follows. So we actually say that strict complementarity condition holds if exactly one of lambda I or Ci is 0 for each inequality constraint. Okay? In other words, we have the multiplication lambda I Ci star is 0, right? So it is possible that this part is 0 and this part is 0. And it is also possible that both of the two parts 0. So strict complementarity condition basically says only one of these two parts can be 0. Okay? In other words, by the strict complementarity condition, we can know that if this constraint is an active inequality constraint, then we can have the coefficient lambda I strictly greater than 0. Now, we have some remarks about the strict complementarity condition. With this property, it actually makes us to analyze the optimality condition more easily. And also, if the strict complementarity condition holds, then the numerical algorithm may perform better in general. Now, let's take a look at an example to demonstrate the first-order optimality condition. We have nonlinear functions here, and we have some non-smooth constraints. Okay, so recall that we got the absolute value of the two components to be smaller than or equal to 1. And to formulate this problem into a smooth optimization problem, we have introduced the technique before in chapter 4, I think, and then we can get the following problem. We got objective function and we got 4 smooth constraints. All the smooth constraints, they are inequality constraints. Then if we plot them in the figure, it is like this. And this is the feasible region we have plot, which is an absolute value of two terms is smaller than or equal to 1. And we also got a dotted curve as the contours of this function. Then from the figure, you can easily find that the optimal solution is actually achieved at the corner, right corner here, okay, where you got the intersection of the contours with the feasible region. And if we analyze the optimal solution and we take a look at the first-order optimality condition, we can see that at this optimal solution, we can check which constraints they are active. Okay, actually it lies on the two constraints boundary. Okay, so we got C1 and C2 are active constraints. Now let's first check whether the constraints they are linearly independent. Okay, so we take gradient of the two active constraints and we can see that they are indeed linearly independent. Moreover, if we solve the KKT conditions, we can actually see that the gradient of function f can be expressed as the linear combination of the two gradients here with the coefficient 3/4 and 1/4. All right, so this actually shows that the KKT conditions we can satisfy with Lagrange multiplier as here. Now, this is actually the theoretical or mathematical form for the first-order optimality condition. So let's make a conclusion about this part. In this part, we introduce the mathematical form for the first-order optimality condition. We also give the definition for the strict complementarity condition. With this condition, sometimes we can make the algorithm performance better, and it will also make our theoretical analysis more easier. Finally, we present an example to show how we analyze the KKT condition. Okay, we stop here and see you next time.